All right, let's continue on with our discussion of probability with a few more examples. So determine the probability of each of the following. What is the probability that a randomly selected person from Chabot will have been born on a Sunday? So we're going to approach this using theoretical probability. So we're going to start off with a fraction. And in the denominator of that fraction, we're going to think about what are all the possible days somebody could be born on. And there's 7 different days for that. And then we're interested specifically in a Sunday, so that would be 1/7 of the possibilities. And then we would want to go to a decimal on that, so we'll go to the calculator. So I'll bring it in the calculator for that. We do the 1 divided by 7, and we get 0.1429. And we'd probably say that as there's a 14.29% chance that a randomly selected person from Chabot would have been born on a Sunday. And that would be our theoretical answer. One thing I will point out is that makes the assumption that all 7 of those days are equally likely to be a day that somebody's born on. If that's not true, we might do a different approach called empirical probability, and we'll be looking at that a little bit further down the page. When you see these on my math lab, they want you to do them from the theoretical approach that all of those days are equally likely. All right, so moving on to the next one. What is the probability that the spinner shown below will land on the number 3? So here I'm assuming if we took that red dial and we spun it, that it would be equally likely to stop anywhere on the wheel. And there's maybe a bit of a temptation to say, well, how many ways could it turn out? 1, 2, 3, 4, and make a denominator of 4. But you really need that equally likely part for the theoretical to work out, and it seems like the spinner would be more likely to land in the 4 than the 1 because there's more space, and even more likely to land in the 3. So when I'm thinking about the probability, what I want there is all of this portion that is the 3. And there's a couple ways to look at it. One is just visually, how much of the circle is that? And I think if you look at that, you'd see that that's 1/2. Another way you could do it is take the lines that are already drawn and extend those out, and then extend this one out, and make a similar line like this one this way. And I think if we do that, then we have the spinner broken up into equal parts, and there's 8 of them, so the spinner is equally likely to land in any of those 8 parts. But how many of them would be in the region numbered as 3 that we have shaded? 1, 2, 3, 4 of them. So it'd be 4/8, which does reduce to 1/2, which we could go to a decimal and say that's 0.5 or 50%. And I think the 1/2 makes sense with what we saw at first. Half of the places that the spinner could land are labeled as 3. But if you want to do it from a counting point of view, then you need to make sure the pieces that you're counting are all equal size. So kind of drawing those lines, kind of a common denominator thing in a way, but just doing it visually. All right, let's move on to the next one. What is the probability that the sum resulting from rolling 2 fair dice would be a 7? So this question's a little tougher than than you might think at first. And one of the things I would point out is a pretty popular casino game would be the game of craps. And they roll 2 dice in that game and look at the sum, and 7 is kind of the most important game in that, the most important number in that game. Lots of people play that. Maybe you've played it before. So I would encourage you to pause the video and see if you can answer this question on your own. It is a little tricky, but give it a try. See if you can figure it out. And then once you've got a try, go ahead and resume the video and I'll show you my approach. All right, so I think the thing that's tricky about answering this question is it's really hard to imagine the equally likely possibilities in your head. Like on this one, we drew them. Here, there was 7 days, so it's kind of easy to think about. This one's tougher. So something that you would want to do, and space a little tight for this, but I think you want to list every possibility that could happen on each of the 2 dice and then think about all the sums. And you don't want to just think about it, you want to show yourself so you can do the counting that you need to easier. This doesn't have to be the case, but I'm going to pretend one of the dice is purple and the other one is green. So on the purple die, you could get a 1, a 2, a 3, a 4, a 5, or a 6. And then on the green die, you could get a 1, a 2, a 3, a 4, a 5, or a 6. And then I'm going to think about all the different sums that we could get when we look at those combinations. So if you rolled a 1 on the purple die, then if you rolled a 1 on the green die to go with that, your sum would be 2. But if the green die was a 2, your sum would be 3, or we could get a 4, 5, 6, or 7. If we rolled a 1 on the purple and a 6 on the green, sum would be 7. If we rolled a 2 on the purple and then thought about all those combinations with the green, they would all be 1 higher. The 2 with the 1 would now be a 3, get a 4, 5, 6, 7, and because a 2 with a 6 would add up to 8, that's our last one there. And then every time the number on the purple die goes up 1, the possible sums go up. So this would be 4, 5, 6, 7, 8, 9, 5, 6, 7, 8, 9, 10, 6, 7, 8, 9, 10, 11, and then finally 7, 8, 9, 10, 11, and 12. And there's a pattern to that, and I definitely filled it in using that pattern, but you want to make sure that it makes sense to you, not just from a pattern point of view. So like, why is that a 10? Not just because it was after 9 and before 11, but because it was a 6 on the purple die and a 4 on the green die, and the 6 plus 4 gives us that 10. Sometimes people object to the idea that I have a 2 with a 3 making this 5, but I listed 2 with a 3 again for a 5, because they're saying that's just the same thing. That's where thinking of these as different colors is handy, because it's different to have a purple 2 with a green 3 than a green 2 with a purple 3. Even though the sum is the same, those are different faces showing on the dice. So when you look at how many possibilities there are for our denominator of the probability the sum would be a 7, you look at all the different sums that could happen, not just like different values, but all the ways they could happen. So you have 1, 2, 3, 4, 5, 6 times 6 rows. So there's 36 different combinations of a purple number and a green number. So 36 is our denominator, and then we'd say how many of those resulted in us getting a 7. So 1, 2, 3, 4, 5, 6. So the probability would be 6 out of 36. Sometimes my math lab insists on you reducing those, sometimes not. So if you need to reduce it, you could cancel a 6. Most of the time we're happy to just go to a decimal without reducing. So 6 over 36 is approximately 0.1667. And if somebody was asking me the probability and I was saying the answer, I'd say 16.67%. So you're going to see that come up every once in a while, this probability question about rolling 2 dice and looking at different sums. I would suggest every time you hear that, you take a moment to write out the full sample space for that, listing every possible combination of numbers on the 2 dice. So a chart like this is really helpful for that. All right, so there's another method of probability besides theoretical, which is empirical. And empirical probability, we say if we run a random experiment a large number of times, then we can use the relative frequency as an estimate of the actual probability. And that's good to do when you have a hard time figuring out what all the equally likely possibilities are. I would argue that would probably be a better idea for this question about the probability of someone being born on a Sunday. If it was all just up to nature and, when did the time come, I think maybe every day would be equally likely. But sometimes for medical reasons, a woman might have to schedule a C-section to have her baby. And if you think about that, maybe the doctor's not so likely to schedule that for a Sunday. So maybe a Monday or a Tuesday might be a day more likely for babies to be born, because when the doctor is involved in choosing the day, maybe they're less likely to pick a Sunday. So empirical probability would say the approach to answering that would be to just look at a large number of birth records and see what percentage of babies are born on Sundays and use that as an estimate for the actual probability. So let me show you a few examples where we take that approach. What's the probability that a baseball player with a .300 batting average, what's the probability of them getting a hit in their next at bat? So usually in baseball we'd refer to that as a 300 batting average. They don't tend to say the decimal. But what that number is just a relative frequency where the numerator is the number of hits and the denominator is the official number of at-bats. So this is a relative frequency for the person getting a hit, and that relative frequency could be used as an estimate of the actual probability. So I would say the probability that that person would get a hit in their next at-bat is just 0.300. So that relative frequency just becomes my probability. Maybe it would make sense to put the approximately equal there because I know since I'm using a number from a sample, it's just an estimate. But that would be my best estimate of their chance of getting a hit, is looking at their past performance and what was the relative frequency. That can come a little bit different, but this is still very similar. During the 2015-2016 NBA season, Stephen Curry for the Golden State Warriors, World Championship Golden State Warriors, made 402 out of 886 three-point shot attempts. So based on this, what's the probability that he would make his next three-point attempt? So assuming that shot came at some point in time right after we had collected this data, our best estimate of the probability of him making a three-pointer, our best estimate of that would come from the relative frequency. So how many of those did he take in our data set? 886. How many of them did he make? 402. So what is the relative frequency? 402 divided by 886, which is about 0.4537. So then I'd say there's about a 45.37% chance that he would make his next three-point shot. So that's how empirical probability works. We're not just thinking like what could happen. If you think of the possibilities, he could make a shot or he could miss a shot. So you might think it's 50-50. But you know, some players are more likely to make that shot than others, Steph being one of the better three-point shooters. But how do you figure it out? It's not just by make or miss. You have to think about how good they are at it, and the only way to really start figuring that out is to look at what they've done in the past, and that provides an estimate for their true probability. And then a follow-up to that, if you were to look at his next 87 shots, how many do you think he would make? Well, what you need to remember there is that probability is an estimate of future relative frequencies as well. So if in the past he's made 45.37%, or if the probability is 45.37%, then we would estimate that he would make about 45.37% of his next 87 shots. So what we do there is we take the 87 tries and we multiply that by the probability of a make, 0.4537. And then we're doing 45.37% of, or times, 87 shots and looking to see how that comes out. So taking the 0.4537 times 87, I'd change the order there, but order doesn't matter on multiplication. We'd say that's going to be about 39.47 made three-pointers. There's a couple things you could do there. You could take that number and say, well, it doesn't make sense to say he's going to make a decimal number of 3, so I'll change that to about 39. But you'll find out later in statistics we consider this to be sort of an average, and even when the result can only be a whole number, it still makes sense to talk about the average as a decimal. That's still possible. So you don't have to change that to a whole number, but that would be a reasonable thing to do as well. I'd just go ahead and leave it like this, and I would use in my answer the word about, because there's no way he's going to make that many exactly. So I would say he'll probably make about 39.47 of them, meaning it'll be nearby. Maybe it's 38 or 39 or 40 or 41. Those are all reasonably close to that. And it is, after all, a random sort of experiment, so we wouldn't expect it to come out just as the probability estimated anyways. From game to game, he'll have different level of performance. All right, continuing on, let's go ahead and look at some properties of probability. And then we will also do some more examples. So the probability of an impossible event is equal to 0. So that's the lowest probability you can ever get for a probability question. If it's absolutely impossible the event could happen, the probability would be 0. For a sure event, the probability is equal to 1, and that's the highest probability that you can ever get for an event. So probability of any event is somewhere between 0 and 1, inclusive. Inclusive means the endpoints are included in that conversation. So we're saying 0 and 1 are possible answers, or anything in between. So any probability question has to have an answer in that range. If you get a negative answer, it's wrong. If you get 1 point something or anything bigger than that, it's wrong. Probability has to be between 0 and 1. So think about that when you get answers, and if you ever get something negative or bigger than 1, you know it's wrong. So go back and look at your work and see if you can figure out what went wrong. And then the last one, the sum of the probabilities of all the single outcome or simple events in a sample space is equal to 1. So if you think of all the simple things that could happen, things that only happen one way, you could find all those probabilities and add them all up, and the total probability should equal 1. All right, and we can take advantage of that sometimes when we choose to use subtraction, and we'll see some of that as we move forward. So let's look at an example. 1,467 randomly selected adults were selected and asked how many times per week they visit quick service restaurants. Use the pie chart of the results to answer the following questions. So we have this pie chart. You can look at the colors to kind of match things up here. Less than once a week, 17.67% is this blue wedge. And you could look at it just to make sure that they kind of match up. But we'll end up answering everything just from these percentages. But notice the biggest percentages are the biggest slices of the pie. So we have, looks like once a week is the biggest answer. And then this green wedge, which looks like a little bit less than a fourth, is the next biggest answer. And notice when we look that one up for twice a week, it is a little less than a fourth, or 25%. But you can just look at the numbers as we answer the questions. That's what we'll end up doing more than looking at the size of the pie wedges, but they should match up. So find the probability that a randomly selected person from this survey group of these 1,467 people visits quick service restaurants more than 4 times a week. So I would argue that what they're listing over here is the relative frequency, but the relative frequency is also our probability. It's the same calculation. This is how many people were like that divided by the 1,467. So somebody's just done that division work for us already. So I would say the probability of more than 4 is equal to that 6.7%, but I would say keep in mind we usually write probability in decimal form, so if we move the decimal 2 spots to the left and got rid of the percentage symbol, that would be the standard way to write that probability. So the probability answer is essentially just sitting there for us, and our job is to write it in the normal probability way, which would be decimal format instead of percent. Let's look at a couple more. Find the probability that a randomly selected person from that survey group visits quick service restaurants less than twice a week. So let's see, less than twice a week is not directly listed here, but I would argue that it's these combined, because if it's only once a week, that's definitely less than twice. If it was less than once, that's also less than twice. But if it was twice, that is not less than, and certainly not 3, 4, or more. So it's those two categories. So I would add them up, 17.6% plus 31.7%. And let's see, a little bit of, not too bad, a little messy. I'll bring in the calculator. 17.6 plus 31.7. Let's see, 13, carry the 1, 9. Should be 49.3, let's see. Yeah, make sure to keep the brain sharp. Try and do it in my head, even if I am using the calculator. And then I would just say, because of probability, we should probably write it in decimal form at the end. So 0.493. So if they give you a word description and it's more than one of the categories there, then just add those percentages together. We'll talk about that a little more as we continue on in the packet. And then the last one for this pie chart, find the probability that a randomly selected person from the survey group visits quick service restaurants at least once a week. So at least once a week. So that would be once or more, right? So that would be once a week or more. So that would be all this stuff that is kind of circled in purple. I don't know, but circle, got a corner on it. But anyways, right? That's what we're talking about. So there's two approaches you could use. One of them would be like we just did. There's 1, 2, 3, 4, 5 categories that meet the description. Just add them up. But the other thing we could do is, since there's only one we don't want, is we could subtract. And I think that would be a better approach. So I could say, let's see, the total of all that is 100%. And I want all of that except for the less than 1 week. So if I got rid of that 17.6% from that group, that should be what I'd get if I added all those other ones together. And doing that subtraction, I believe, would be 82.4%. So I think that's a better approach than adding all those up. That's a really key thing in statistics, is to remember that adding is one way to get there, but you can also subtract what you don't want. We're going to formalize that as a rule in a little bit, but it's definitely something to be thinking about already. And then since we did this with all the other ones, we should probably change that to 0.824, write it in as a decimal, because that's typically what we do for probability. I'm just going to drag the calculator in here real quick and double check that by adding the other 4. I don't think we need to do that, but we can just as a double check. So 31.7 plus 24.1 plus 14.4 plus 5.5 plus 6.7 is 82.4. But again, faster to get there through subtraction. They both work, but try and go the fastest, most efficient way if possible. All right. So moving on to another definition, we're going to look at a random variable. And a random variable is a numerical measure of an outcome from a random experiment. And we often use a capital letter such as X to stand for the random variable. So for example, a while ago we were talking about rolling 2 dice and looking at the sum. One of the things you could do with a random variable is say let X be the sum when you roll 2 dice. And then if we happen to roll a 2 and a 5, we'd say X equals 7. If we happen to roll a 6 and a 3, we'd say X equals 9. But how you figure out X is not to solve an equation, it's to do the experiment, to roll the dice and see how it turns out. So that's how random variables are set up and how they work. So we'll look at an example of that on the next page. All right, so continuing on, here's that random variable example I promised. The number of days it took Chicago's Department of Streets and Sanitation to respond to requests to fix potholes are described by the density histogram shown. Let X equal the response time to fix a randomly selected reported pothole. So one of the things we need to remember about density histograms is that in a density histogram, the area of a bar, which they've labeled for us on most of these, is equal to the relative frequency for that category. So what they're giving us, they're calling density, it's really relative frequency, but relative frequency calculations are the same as probability calculations, so we can substitute them back and forth. And then I guess since these are areas, you could even say for density histogram, the area of the bars represents probability. And that idea that area can represent probability is really important as we move into stat class next semester. So it's good to kind of get used to it here. So find the probability that X is less than 7. So we just look at the graph, and this would be 0 to 7, so the area of that bar is 0.34. That's the relative frequency, but it's also the probability. So we're just looking at the histogram, trying to find the bars that match up with what they're describing, and then use their areas to get our probability. Determine the probability that X would be between 7 and 21, including the 7 because of the extra line, but not the 21. So on a histogram, the number that's on the edge of a bar is part of the bar to the right, not the bar to the left. So this 21 is not included in this 0.12, it's included in the 0.08 bar. So from 7 to 21 would be from here to there. So it looks like there's 2 bars that fall in that zone, and they have areas of 0.33 plus 0.12, and they're areas, right? And they're asking for probability, but remember, area on a density histogram is the same numerical calculation as probability, so we're going to use area of density histogram to answer probability questions. And then we have 2 of them, so we'll just add them together, so that's 0.45. All right, so now let's interpret those results in Word. I'll do both of them. This one is the probability that X is less than 7, but X is the response time to fix a randomly selected reported pothole. So if you found a pothole on your road and you lived in Chicago and you called in there, you would expect that there's about a 34% chance that they would take care of that in less than a week, right? In less than 7 days. So what would that be here? If you had a pothole on your road and you called in and asked for it to be fixed, there's about a 45% chance that it would take at least 7 days, but less than 21 days. So somewhere between about a week and almost 3 weeks. So interpretation, there is a 45% chance. When we talk about probability, we generally convert it back to a percentage, that it will take somewhere between 7 and 21 days until a randomly selected pothole that has been reported will be fixed, repaired, whichever word you want to use there. I guess cleaning this up a little, between 7 and 21 would not include the 7, so we should point out that this one is included. So from 71 to less than 21 days might be a little bit better way to say that, to match up with the or equal and the strictly less than. So I don't know, why not? We can fix it right here. Drag in a new color. It'll be somewhere from 7 to less than 21 days. I think that's a better fit for the symbols. The words that I had there between 7 and 21, those words are not inclusive. That would have been great if there was less than on both cases. So this is a little bit better. Let's try another one. Determine the probability that x would be greater than 42. So let's go look at our picture and think about where that would be. So x is greater than 42. Here's the 42. We want all of these bars right here. So we'd want to look at their areas and add them together. But they didn't give any of them to us, so we can't do it that way, right? But one of the things that we should know about a density histogram is that if you added the probability or area for all those bars, the total should be, think about it, it should be a 1, right? So if you want these missing ones, you could take the total of 1 and you could subtract all the stuff that you don't want. So we don't want any of these bars to the left, so if we subtracted all of them, the 0.34, the 0.33, the 0.12, the 0.08, the 0.03, and the 0.07, then if you subtract those away from the total, remember 1 is what you'd get if you added all the bars together. So if you subtract this away from the total, you should be left with these. So that's the approach we would have to use on that one. So let's see how that works out. So 1 minus the 0.34, the 0.33, the 0.12, and so on. And we get 0.03. I would just think about it real quick to see if that makes sense. That's a pretty low probability, but those are all very short bars, so that could be a reasonable answer to that, I think. So 1 minus 0.34, 33, and 12, and 08, and 03, and 07. Just double checking those all real quick against the bars. Looks like we did that right. And interpret that result in words. So we're talking about the probability of the time it takes to fix a pothole, and we're saying it's about a 3% chance. So kind of going off the model from right there, there is a 3% chance that it will take, let's see, this is the time it takes, more than 42 days, so it will take more than 42 days until a randomly selected pothole that has been reported will be repaired. And just our luck, that's probably the one on our street, right? It's not very likely that if you reported a pothole on your street in Chicago that it would take, I think that's 7 times 6. So that would be like 6 weeks, a month and a half to get that pothole reported. That doesn't happen too often, but 3% of the time when somebody reports that there's a pothole on their street, it can take that long. Kind of unusual, but it does happen. All right, so the key thing we want to remember from that problem is when we are working with a density histogram in a probability context, the area of the bars can be used to answer probability questions. And that idea that area and probability can be interchanged somewhat is a really key concept in statistics. We end up using that to answer lots of probability questions. Most of our probability questions in statistics get answered using area, so that's definitely something that you will see again. All right, continuing on, in this section we're going to look at the complement and addition rules that get used in probability calculations. So according to the information shown to the right, what is the probability that it will not rain on Friday? So we have to kind of figure this out a little bit. They're saying in this city that it's going to rain on Friday night, maybe. And they're showing us a raindrop right there and saying there's a 30% chance of it. So that's our probability that it will rain that night is 30%. So what's the probability that it won't rain? So they don't list that, but I think that it's fairly intuitive to say there's a 100% total possibility. So you can subtract that 30% away and say that there's a 70% chance of it not raining if there's a 30% chance that it will. If you did that in probability form, the 100% would be a 1, the 30% would be 0.30, and when you subtract, you get 0.70. And doing it in that decimal form is the way that we have our rule written out that goes with that. I think this is intuitive to do it in the percentage way, but this is just the same thing written in decimal form. So the complement of an event is the event that consists of all the outcomes that are not in that event. So if the event, throw T in there, if the event E, the complement of the event E is all the things that are not in E. And the way we write that is by writing the word not followed by the event. So here's an example, probability of not E. And if you were to think about that in terms of a Venn diagram, E is inside of this circle and inside of the box. Not E is going outside of the circle but still staying inside of the box. So the box represents our entire sample space, everything that could possibly happen when we do the experiment. And when we say that it's not E, it's just subtract away everything from that center. So, but subtract from what? The total. And in probability, the total is 1. So the probability of an event will not happen is 1 minus the probability that it will happen. And so that's known as the complement rule. It's kind of intuitive in the sense that I think without knowing much about probability, if somebody told you there's a 30% chance it's gonna rain, what's the chance it won't? I think most people would subtract that from 100 and say 70%. This is just formalizing that with some probability notation. All right, so let's think about that. What is the probability that the next person you meet will not be born in July? So what we would want to do there is say the probability that they won't be born in July is 1 minus the probability that they would be born in July. And they want us to do this from the theoretical point of view. And even though all the months are not equal in their number of days, when they ask you this type of question in my math lab, they just want you to think of it as 12 months. I think this is a little distorted because July is a longer month than February, right? And then we're not even positive that people are equally likely to be born in all the months. But what they want us to do here is take 1 minus the probability of July and to think of July as 1 month out of 12. And then you could say that's 12 out of 12 minus 1 out of 12, which is 11 out of 12. But we usually go to a decimal anyways. So you could go to a decimal without doing the common denominator work, just 1 minus 1 over 12. If you wanted to do it as 11 twelfths, it would be the same. But you can save yourself the fraction work. If you know they're going to a decimal, as soon as you get it written out some way as a fraction, you could go to the calculator and get 0.9167. So there's about a 91.67% that the next person you kind of randomly come across would not have been born in July. assuming that people are equally likely to be born in all given months. I think that's probably a little flawed. That's why empirical probability would probably be better here. Go look at birth records and see what percentage of people are born in July and subtract that away from 100%, or subtract it from 1 if you're doing this as a decimal. Probably more accurate than making the assumption that every month is equally likely. But that is what they want you to do in my math lab, so I'm going to show it to you that way. All right, another definition that'll lead to another rule for us. Disjoint events. Two events are disjoint or mutually exclusive if they have no outcomes in common. So for such events, or questions can be answered as follows. Let me draw you a picture first before I give you the rule. If we drew a Venn diagram, disjoint events are separate. There's no overlap. So you have an event A over here, and you have an event B over here, but there's no outcomes in common, so there's no overlap like we talked about with our Venn diagrams earlier. And when that's the case, it turns out that you can just do the probability of one of them and add the probability of another one. And so we could do that for our quick service restaurants problem that we did earlier. If they ask us for a probability about things from this list that are not overlapping, and I think if you read these carefully, you'll realize none of them are overlapping. There's no outcomes in common between any of these different pieces. That's why they're separate wedges of the pie. Okay, so let's go ahead and try out this rule on this pie chart question. So use the pie chart to determine the probability that a randomly selected survey respondent visits quick service restaurants at least 3 times a week. If that's not already written on your handout, please fill it in. That was an initial mistake. But at least 3 times a week means 3 or more. So that would be all these groups. We already kind of did something like this before we even had the rule. It was kind of intuitive. We just added those together. This rule officially says that's okay to do. If there is no outcomes in common, then you can just add the individual probabilities. So that probability becomes 0.144 plus 0.055 plus 0.067. Now I switched those to decimals in my head as I wrote them down because we tend to do decimals for probability. You don't have to do that first. You could just add up the percentages and then convert to a decimal at the end, but eventually you'd want to convert it. And I've done a lot of these, so I feel pretty comfortable just doing those conversions quickly in my head as I write it down. 0.144 plus 0.055. That's often a tricky one for people. They just want to move the decimal to the front and say 0.55, but that'd be 55%. That conversion is always moving 2 places. And then plus 0.067. So it looks like 0.266. So if I was going to interpret that, I would say there's a 26.6% chance that a randomly selected survey respondent would visit quick service restaurants at least 3 times a week. All right, let's look at our spinner example again. Use the graph to determine the probability that the pointer will land on an even number. So we could shade the even numbers. We've got 4. And we've got 2, so that's the part we want. Again, you have to be a little careful there. You can't just say that's 2 out of 4 possibilities because they're not the same size. So we'd want to chop it up like we did before, drawing in the extra lines to make all of these the same size. And when you do that, it looks like the size is 1, 2, 3, 4, 5, 6, 7, 8. So each one is an 1/8. And then how many do we have shaded? Well, for it to land on the number 1, well, first of all, we could say this. That's the probability of an even number. For this particular spinner in the possibilities is the probability of 2 or 4. But then using our rule up here, because those don't overlap each other, they don't have outcome in common, we could do them separately. The probability of 2 plus the probability of 4. And then we could look at the shading and say, what is the probability of 2? That's 1/8 of the area of that spinner, plus 4, which is 2/8 of that area. So altogether, the probability would be 3/8. And then we generally would go to a decimal on that. So if you do 3 divided by 8, you get 0.3. 375. So there'd be about a 37.5% chance that that spinner would land on an even number, meaning either 2 or 4. But we did use this rule up here to do it. They're disjoint because they don't have any outcomes in common. They're separate parts of the spinner. And then we just added the two probabilities separately, though it is important on the spinner type situations to make sure that when you think about the probability, you're not just thinking about possibilities, but equally likely possibilities. And we get that from cutting up the spinner into equal size segments, 1/8 of which were 2, 2/8 of which would be the 4 for 3/8 altogether, or 37.5%. All right, so we just saw that if things are disjoint, we can add the two probabilities separately, but you can get into trouble if you tried to apply that rule when things are overlapping each other, when they do have outcomes in common. If you were to do that, if you were to take all the things from A and add those up, and then you were to go back and add all the things from B, you would get everything you needed, but you would double count this overlap wedge. So we want to be careful that when we do the counting on the green, we kind of stop that on just the new stuff. That we just take this little wedge out right here and we say, count all the stuff in A, yes, but when you count B, just count the new stuff. So the general addition rule states that if you're trying to find the probability that one event or another event will occur, then if you were going to think of that as a formula, you would want to think about the probability of A, but then when you do the next one, you'd want the probability of B, but you'd want to subtract out the probability of the overlapping part, which we call an AND. Not that you don't want the overlap, but if you count A and B, you count that twice. So this is the way they usually write the rule: count all of A, count all of B, and then subtract the overlap. I like to think of it with like parentheses around this part, or brackets. Count all of A, but when you count B, don't count the overlap. Don't count it, right? Subtract, because you already have that part. Only count the part of B that wasn't overlap. So in words, when two events are not disjoint, so they have something in common, you have to worry about this double counting problem. So we should determine the numerator of that probability by counting all of the outcomes in the first event, every one of the things in A, but then only adding in outcomes from the second one that have not already been counted. So only the new stuff when you move on to the second event. So that's real important. Keep in mind that you don't double count. The rule could say double count and subtract the extra. I think you'll do better in probability if you avoid the double counting in the first place, and the words version tells us that. All of the first one, but only the new stuff from the second one, only the stuff that has not already been counted. When we're asked about an AND, all this stuff we've been talking about so far, where we're adding things together, is for OR questions. What if they ask you an AND? Well, the first thing you need to know is, how do you visualize an AND? If somebody says, I want the probability of A and B, what are they talking about? And the important thing to realize is that they're just talking about that overlapping part. So the probability of A and B, we might write that also with that symbol, is the probability of the overlapping part. So let's go ahead and try and think about some examples of using AND and OR, and thinking about this, and also thinking about maybe if they're disjoint, how that would play into. So we'll start off with some simple things and then go to something a little bit more complicated and see how it works there. So consider the roll of a balanced die. Find the probability that the number you get is odd and it's less than 5. So visualizing, I think, on these things is helpful. So I would write out the sample space. If you roll a die, you could get a 1, a 2, a 3, a 4, a 5, or a 6. So just kind of visualizing everything that's possible. When you do that, you've kind of sorted out what your denominator is. But now for the numerator, when it's an AND, you only want to count the overlap. So let's do the odd numbers, 1, 3, and 5. And then let's do the ones that are less than 5. The words less than are not inclusive, so that would just be 4 and down. But it's an AND, so we want the overlap. So we want things that are overlap to being circled in kind of this maroon and also being circled in the purple. So the 5 is only in maroon, the 4 is only in purple, but the 3 is in maroon and in the purple, so that's part of the overlap, and the 1 is in maroon and the purple, so that's part of the overlap. So out of the 6 numbers, how many of them met both the description of being odd and being less than 5? Just the 1 and the 3. And so that would be 2 out of 6, or 1/3, or approximately 0.3333. Let's try that again, sticking with the idea of the die. So consider that you roll this balanced 6-sided die. What's the probability of getting an even number or more than 3? So first of all, let's list the sample space. 1, 2, 3, 4, 5, 6. Those are the things that can happen when you roll the die. And then let's mark off the events. So even numbers, 2, 4, 6. And then the other one is more than 3. So more than 3 does not include the 3, so that would be 4, 5, 6. The way an OR is different from an AND is instead of just counting the overlap with the OR, you count all of the first one, and then from the next version, just go to stuff that hasn't been counted yet. So let's think about, first of all, our sample space. There were 6 numbers, so the denominator is 6. And let's count all of the ones that were even, which are the ones I circled in the kind of purple. 1, 2, 3. And then add on anything that's in the green circle, but only if it has not already been counted. We've already counted the 4 and the 5, so the only new thing is that one number right there, the 5. So when you do an OR, count all of the first one, 1, 2, 3 things circled in purple, and then say, is there anything new in the green I don't have yet? Yeah, there's one number there that's new that I don't have yet. And so we get 4, 6, which is 2/3, which is 0.6667, or 66.67%. All right, let's look at one last of these. Consider rolling that balanced die. What's the probability that what you get is not a 4? So again, what's our sample space? 1, 2, 3, 4, 5, 6. And I just want to point out the use of the complement rule here. When they say what's the probability that it's not a 4, we could just think about what that is, what number it could be. But according to the complement rule, we could take the total of probability, which is 1, subtract out the probability that it is a 4, and that should give us the answer 2. And if we do that, we do 1 minus the probability of a 4, and a 4 is just 1 out of the 6 numbers. If you do that with a common denominator, you'll come up with 5, 6. When you go to the decimal, you have a choice. If you did the common denominator work, you might as well enter in the 5, 6 to get the answer. But if you just wrote it out this way, that would be good enough too. 1 minus 1, 6, you get the same decimal. So 0.8333. So always good to remember this idea that when somebody says what's the probability that you don't get a certain thing, you could think about what does it mean to not get a 4? It could be a 1, a 2, a 3, a 5, or a 6. That's 5 out of the 6 numbers. But you don't really have to think about what the other numbers are. Just subtract out the probability of it getting a 4. But subtract from what? From the total. And then when you're doing probability, the total is 1. All right.